optimized Genesis sequence.
Is audio on? No, now it is. Hello, everybody. Welcome to Accelerating Performance of Java Applications on Arm64. My name is Dave Neary. I run developer relations for Ampere Computing. CPU provider, we make Arm64 CPUs. That's why I'm talking on this topic. And today I'm going to talk, essentially this is a talk that's going to be in two parts. There's going to be a bonus part 0 where I'm going to talk a little bit about why you might consider Arm64 as an architecture for your application deployments. The first part is going to be about how OpenJVM improved in performance between Java 8 and Java 21, I guess, by a significant amount, 30% on Arm64 over the x86 port. We're going to basically break that down. This is going to be Arm64 specific for the most part, about 50-50. But we're going to talk about the work that's been done in Project Panama and intrinsics. We're going to talk about the differences between x86 and Arm64 atomic instructions and how that can affect performance. We're going to talk about SIMD on Arm64 and how that's been used to accelerate JVM functions. And then we're going to have a little bit of conversation about memory barriers, what they are, why they affect performance, and how that's essentially been the lion's share of the effort that goes into accelerating performance on Arm64. In the second part, this is not going to be very platform specific. It's going to be how you, running Java applications on Arm64, but the same advice applies to x86 for the most part, can get better performance out of your applications running in the cloud. So I'm going to be mostly focusing on, once applications have gotten off your desktop and they're running as server applications in the cloud. We're going to talk about choosing the right garbage collector, setting your heap size appropriately. We're going to talk about some of the JVM configuration options that can dramatically affect performance, but we're also going to talk about operating system configuration that really needs to go hand in hand with JVM configuration if you want to get the most out of your application. If there's a few minutes left, we'll have some time for questions. So to start off with, why are we even talking about Arm64 or AArch64 today? So for those of you who don't know, Arm64 has been a port in the JVM for 10 years now. But really in the last 5, 6, 7 years, we've seen a dramatic increase in interest in and deployments of applications on Arm64, primarily driven, I would say, by the popularity of Raspberry Pi, by the adoption of Arm64 as an architecture for Mac laptops, M1, M2, and in the cloud, we've got Graviton on AWS and Ampere pretty much everywhere else. Have made Arm64 instances widely available. So for example, if you get an Arm64 instance today on Azure, on Google Cloud, on Oracle Cloud, what you're getting is Ampere under the covers. If you get it on AWS, obviously you're getting Graviton. And that will change in the future. I don't want to talk too much about the proliferation of Arm64 chips for clouds, but there has been a massive groundswell of interest in running applications on Arm64, and that's primarily for 3 reasons. These cloud CPUs, these CPUs that are very high core count, very low power, and very performant cores, have been designed from the ground up for the needs of cloud computing. So for example, some of the things that are legacies of the desktop era, simultaneous multi-threading. Arm64 cores in the cloud typically are single-threaded. Ampere cores are all single-threaded. What that means is that you're not suffering from resource contention because you've got 2 virtual threads running on a single physical core. We're low power, which means that you get to have more cores per rack. Low power means less heat. Less heat means easier cooling. It means that you have more server density in the rack. So in a 42 rack, you're going to be running maybe 35 U occupied instead of 21. And it means you can get basically more compute per cubic meter. So it's kind of, for cloud vendors, it's a real estate play. But for application developers, it's also a financial play. Because we provide more CPU cores per socket, and you've got more sockets per rack, you've got lower operating cost for those cloud providers, which means that they can pass on that cost saving to you as lower cost per core hour when you're renting those instances from a cloud provider. And finally, it's good for the planet. I talked about low power already. Right now, this is kind of a big deal, but I don't want to spend too much time on it. Right now, about 3% of global energy production is being spent on data centers. With the rise of AI, that's going up. It's expected to trend to about 10% of global energy production by 2030. Right now, over 20% of Irish energy production is going to data centers. So that's a massive deal, and it really does have a real-world impact when you think about the fact that the demands that data centers are putting on electricity grids, particularly in Europe, where we're more densely populated than the US. You know, there's a lot of land in Iowa. There's not so much in Ireland or the Netherlands or Germany. We're starting to see a trade-off happen in terms of city planning, where you need to think about how many houses can we afford to have added to the grid in the next 5 years if we're going to have 5 more data centers. So it's really transforming the way we talk about energy and the way we talk about the cloud, AI, et cetera. So these are some of the reasons why ARM64 has gotten a lot of traction recently. Okay, so let's talk a little bit. This is going to be, the first part is going to be more ARM64 specific. Let's talk about how OpenJVM's performance has improved between Java 8 and Java 21. First, the JVM has gotten faster. This is an Oracle chart. It shows throughput scores and latency scores on spec.jbb, I believe. And you can see that the performance in terms of latency, I believe the latency score has doubled, so half the latency at increased throughput. Basically, Java 21 performs a lot better than Java 8. You should be running a more recent JVM. If you're still on Java 8, there's a problem. And JVM support was new for Arm64 in Java 8. So on JVM, we've seen an even bigger improvement, right, on latency, on the latency score. It has basically, we've got triple, so it's 300% the score, which is 1/3 of the latency, I believe. And there are a number of reasons why there's such a dramatic performance improvement on ARM64, and we're going to break that down into 3 families. I'm going to give a few examples of specific patches that use each of these families, but in general, we've got general performance improvements in terms of we've got better GCs for latency with ZGC. We've got some language features that have been added that have improved performance of things like string operations. We're going to talk about some of the more platform-specific generics, things like SIMD, atomic instructions, memory barriers, and then finally we're going to talk about some ARM64 specific optimizations. I'm sorry, I just repeated myself there. Okay, so let's start with the power of intrinsics. So an intrinsic function is essentially the JDK calling out to, or the JVM calling out to a native application library. For a number of key operations, things like string operations, the native system string libraries have been highly optimized, right? Memory functions, highly optimized. So if you have an example, the JDK can call out to native functions for a bunch of stuff. And in particular, I'm going to talk about string and memory functions. An example function, something like index of, highly optimized on the operating system, so we don't use a Java implementation anymore. You're going to call out to system implementation. And Project Panama is the JVM, is the OpenJDK project that kind of overall has done a lot of work on using system intrinsics to the extent possible to improve performance of the JVM. One example to call out compact strings. This is relatively new, obviously. I don't know if it's obvious, but strings in Java traditionally have been 16-bit characters, an array of them. Compact strings is essentially, by default, you're going to use an array of bytes. So if your string is 8-bit clean, then you will use a memory structure essentially that's half the size. That reduces your memory usage. It also increases performance of functions that are operating on that. So in typical usage, it's between a 5 and 25% heap reduction and a 5 to 25% performance improvement. But that's just one example, and there are many, many more. And you can actually see for yourself, running your typical Java applications, what intrinsics are being used with diagnostic VM options and print intrinsics. Okay, but to get a little bit more specific about ARM64, so single instruction, multiple data. What that is essentially if you're doing the same operation over and over again on the same type of data, something like, for example, manipulating an array or image processing is a classic example. You have essentially the ability to do that operation once if you concatenate the integer types that you care about, concatenate them into an array, and then just a single operation, you're going to do your multiplication, division, complex addition, complex division, whatever that operation is. So on ARM64, a lot of the implementations of this were relatively new over the last 10 years. Vectorized instruction sets have been common on x86 for a long time with SVE. But in ARM64, we use Neon as the SIMD instruction set. And there's a wide array of things for a classic example, again, is kind of cryptography, encryption, decryption, where you can create this array of integers. You're putting a multiple number of these integer types together, and then you apply the operation a single time. In practice, these are instruction set, like assembly level operations, but what happens is that they get compiled from C intrinsics, and what's been happening is that the JVM is creating Java implementations that call out to those C intrinsics. And you can get significant performance improvements. This is a single example from a colleague of mine. This is from FFmpeg. This is not a Java example, but this is a single algorithm that was a deinterlacing feature of AV filter for video streams. And simply changing to a Neon implementation of the algorithm increased the performance by up to 3x on ARM64. So this is a simple example to show that there are massive improvements to be gained by creating Neon implementations of algorithms like this. And there are many of them in the JVM, particularly in the cryptographic libraries and so on. Okay, so I'm going to talk a little bit. This is an example of how something that's a feature, not a feature, something that is a behavior pattern in ARM64 that is different from x86 that actually caused a performance slowdown. And I'm going to walk you through it because I think it's an interesting example of kind of the intricacies of these performance issues as they refer to the architecture. Okay, so let's talk about what an atomic instruction is. These are essentially instructions that allow you to do to make a change to a register in a single step. So you can read a data type from a register, modify it, and store a new data type back to it, and have a guarantee that nothing has changed in the meantime. They exist to essentially provide a guarantee that when there are multiple observers that can be looking at the same data source, that they don't see two different values. How they work in ARM8, and I'm specifically not going to talk about large system extensions for anybody who's familiar with ARM64 here, but how they work in ARM8 in general is by what's called an LLSC, atomic operations. So the atomic operation itself is split into two parts. You've got a linked load, which reads the value and marks that register for observation. And then you've got a conditional store, or a store conditional, which before it writes the store will verify if something has changed in the register. So if we look at this code example on the right here, we start with the LDA-XR is the load and acquire exclusive register. So that's the load the value from X0 into the special register W8. and then we're going to mark x0 for observation. And then when we get to writing back to that register, we use the STLXR, store release exclusive register, which is going to try to store W8 and x0. But if x0 is changed, it's going to return an error code, and we can verify whether that error code is 0 in a success, and if it's not, then we branch back and we try again. So that's how atomic instructions work in Arm8. Typically, Java developers don't come across atomics very often, but if you are using some kind of locking like synchronized code blocks or volatile types, then you're going to have some kind of, oh no, I'm mixing things up. That's memory barriers later. Okay, so before we talk about this particular bug, we're going to take a 10,000 feet view of memory management, like literally 1 minute overview of things on which books have been written on. Essentially, applications that are running in an operating system, Linux in particular, are going to have a virtual memory space. That virtual memory space has the program code in memory, and then it's going to have the stack that that program generates as it's running. It's going to have the heap that that contains data generated by that application. That virtual memory is carved up into memory pages. On x86, those are required to be 4K. On Arm64, you actually have some flexibility in there. Those pages are not initially mapped to physical memory pages. What happens is that memory the memory that exists in virtual memory space gets mapped to a physical memory address as it is used. So those memory pages can be uninitialized, right? I can create data out of whole cloth, and in cases where I'm writing to a memory address that's uninitialized or reading from a memory address that's uninitialized, the kernel will provide me, on my first read, will provide me with this virtual memory page that's uninitialized, a 0 page, and will only actually write to memory when I'm actually writing data to it. It does a copy on write. So at a high level, when a virtual memory address is accessed, but that physical memory address is not in memory yet, we have a page fault. There are two types of page faults. Read faults happen when you read memory for the first time, and a write fault happens when you're storing to memory. The bug we're going to look at concerns always pre-touch, which is a way that you can warm up your application, make sure that every memory page that you're going to need is actually stored in memory. And we're going to talk about transparent huge pages. And I realize this is like hopping all over the place here, but transparent huge pages is a kernel mechanism that allows you to have a single page table entry for a very large block of memory. In principle, contiguous block of memory. It essentially allows you to have, for data-intensive applications, less thrash in your cache, which is alliteration that was accidental. So you get fewer translation look-ahead buffer misses because your page is more likely to already be there, and it allows you faster sequential access across a contiguous block of memory, in principle. Okay, so I'm going to see if you can spot this. In Java 18, the mechanism for pre-touching memory changed on Arm64, but I believe it changed everywhere. What this code does is it goes through every single page in the memory buffer that we want to.
Someone has some YouTube video on is very annoying and trying to concentrate on this. Can you mute it, please, whoever that is? Really?
It's coming out of the other room. I don't hear a YouTube video. So when you're using pre-touch memory, what it does is it traverses all of the memory in the heap and says, I want to write one character into each memory page. And that makes sure that that memory page is loaded into memory. It uses this intrinsic atomic add 0. So it doesn't actually change the memory address at all. It gets an uninitialized page, it adds 0 to the first entry in the page, and that ensures that the memory is in RAM. Okay, this forces a page fault, loads every page into memory. This is good. But I want to see if you can spot the bug. When we're using THP, transparent huge pages, when the page is first referenced, a read fault, the kernel serves a 0 page, a special page that just has zeros in it. It's like reading from dev0. So it serves a transparent huge page that's all initialized to zeros. When you write to a page for the first time, it generates a different fault, a write fault, which does a copy on write and creates an actual physical page in memory and connects that to that page. Can anybody see what the problem is here for when you've got THP in combination with always pre-touch? What happens is that the initial load gives you a huge page that's all zeros, but it's a virtual page, it doesn't exist. But every time I'm writing one character to every page, I'm creating a new 4K page. So what I've done is I've essentially fragmented my huge page into, instead of one huge page, I have 512 write faults being created with 512 4K pages that are all connected that I have to traverse in a page table. So I'm losing all of the benefit of transparent huge pages, and I've got a massive performance overhead in startup with the always pre-touch. So this is an example of a kind of a tricky performance impact of something that you would think, oh, an atomic instruction, that's just like atomicity means it happens as one step, right? But because it happens in 2 steps in ARM8, we have this idiosyncrasy of the read fault and the write fault being generated independently. And the workaround for that is to use a mechanism called madvise, memory advisor, with something that was added in, I believe, the Linux 5X kernels called MADV populate write, which indicates to the operating system, I intend to write to this area of memory, so make sure it's in RAM. That's all it does. It doesn't use any atomic instructions at all. So we actually moved away from using atomics just to improve the performance of this particular feature. I will, by the way, share these slides afterwards. So all of the links and all of the links to JDK patches and so on will be included. Okay, the next big section, and this is something that I've spent a lot of time learning about because this is kind of complicated. I am, by the way, just sharing other people's work here. This is nothing that I've worked on, so I want to make that clear. We're going to talk a little bit about memory barriers. So let me start with a puzzle. I want to ask for a show of hands here, actually. This code, kind of pseudocode on the right, we're going to initialize 2 registers, X and Y, to values 1 and 2, and then we're going to start 2 threads. In the first thread, we're going to write the value 3 to X and read the value Y. In the second thread, we're going to write the value 4 to Y, and we're going to read the value X. So do you think that those reads of X and Y can ever give you the result 1, 2? Who thinks that's possible? Okay, there's about 10% of you that, yes, that is possible. The reason why is because ARM64, like many modern CPUs, has a weakly ordered model. It can change the order of instructions in program order if they don't depend on each other. So in thread 1, reading Y does not depend on writing X. So the CPU can just swap them around, right? It can read Y before it writes X. In thread 2, the same thing applies to reading X and writing Y. So what we have is we don't have this dependency between the read and the write, which means they can be reordered. And because threads can interrupt each other in a rather unpredictable manner, you can have the first instruction in thread 1 execute, then context switch to thread 2, have the first instruction in thread 2 execute, and then go back to thread 1 to finish and thread 2 to finish. So in fact, all 4 possible scenarios here, this can be 1, 2, this can be 1, 4, this can be 3, 4, and this can be 3, 2. All 4 possibilities are possible running this code. So you cannot guarantee ordering, particularly when you've got multiple threads operating on the same registers or same piece of memory. So, as I was saying earlier, memory barriers in Java are not typically something that programmers need to worry about. They do come up very frequently when you're using synchronized code blocks or volatile data types. You're essentially using memory barriers under the covers because you need to protect those areas of code, those instructions. And there's some suggested reading here on properly using volatile and synchronized and how those things translate into memory code. I will recommend. And I have no idea why that went black. So on Arm64, there are 3 special instructions that create barriers. The first is a DMB. This essentially ensures that any explicit memory accesses before the DMB, so stores and loads, essentially, are processed before any explicit memory accesses afterwards. A DSB goes a little bit further, and it's also going to affect things like cache invalidation, branch prediction, TLB maintenance operations. These are also going to be, order is going to be enforced. And finally, the instruction synchronization barrier. So if anyone's familiar here with the way that processors pipeline instructions, a processor running an instruction essentially has a multi-step process. It can be 3, 4, 5, 6. But those things are all, you need to fetch the instruction, you need to decode the instruction for execution, then you run the instruction, then you store the result, then you retire that instruction, you remove it from the processor. So those things can all run in parallel. So when we've, if you've been familiar with some of the more thorny bugs that have affected the computer industry in general, things like Heartbleed in recent years, they all rely on branch prediction and getting information from branch prediction. That's essentially, when you come to a branch point, that's essentially how branch prediction works, is you're going to say, I'm going to guess which end of, which branch of this program gets executed next, and I'm going to prefetch the instructions from that branch. If I'm wrong, I'll fix it later. Okay, so the ISB essentially wipes all that out, says you need to get rid of all of your branch pipeline. It's a costly operation. And that's the key point here, is that these things are costly operations. From least costly DMB, data memory barrier, to most costly DSB or ISB, which can both be very costly. So there are ways to scope them. You can scope these operations to an inner shareable domain, which is essentially a set of CPUs, an outer shareable domain, which is going to be another number of things that can access shared memory or shared resources, things like GPUs and DMA or interrupt generators. And you can further scope by access types. You can scope these memory barriers by stores or loads, or you can have no qualifier at all. So in summary, adding memory barriers can add cost, and they can be applied overzealously. This is what makes them very hard to debug, is the fact that you can have a DSB in a place where a DMB would suffice, and the only effect of that is that your code runs slower. There's no functional effect at all. However, if you have a DMB in a place where you require a DSB, your code can not function correctly, right? There are things that you will get these sporadic Frankenbugs where 1 time in 100 instructions get ordered in a way that gives an incorrect instruction, gives an incorrect result. So removing unnecessary barriers or reducing the scope of the barriers represents a significant performance improvement. And I'm going to call out Alexei Shipalyev who is here, I believe, and helped explain this to me in a way that actually kind of made sense. And Andrew Din, whose names are all over all of the patches for the last 5 years around memory barriers in JDK. And there are some examples here of how you can, in many circumstances, have relaxed memory barriers. And it's important that the JVM uses the least zealous barrier possible so that it's not impacting your performance. Because like I said, having a DSB invalidating all your cache or having an ISB that's going to clean out your instruction pipeline, those are pretty costly operations, and they can slow down your code a lot. This is mostly in the JVM. As a developer, you need to make sure that you're using, if you have critical sections of your code, and it's certainly in multi-threaded code, then you need to make sure that you're using synchronized code blocks or volatile data types correctly so that you don't have this multi-count or multi-observer effect. But for the most part, this is something that Java developers don't need to care about. JVM developers care a lot. This is where we get to the part where Java developers actually do need to care about this stuff. So I'm going to talk a little bit about how you can tweak your JVM performance for maximum performance. And there's very, very little that's architecture specific here. We will talk a little bit about how different size kernel memory pages can impact your performance, but for the most part, this is not going to be architecture specific. And the first piece of advice, and again, I'm going to give credit to somebody else. Bruno Borges gave a presentation last year at this event. It was fantastic. It's tuning your JVM performance, and the default ergonomics of Java are terrible if you're going to be running your application in the cloud. The default ergonomics are essentially created for people who are developing Java on their desktop, and it's not the only thing running in your application, running in your host. So this is the situation. Default ergonomics, if you have between 64 megs and 256 megs available for your JVM, the default heap size in that situation is 50%. Between 256 megs and 512 megs, that does not move. It stays at 128 megs. And once you hit 512 megs, then it's again proportional to the available memory, but it's 25% of your available memory. Now, I don't know about you, but if I'm paying for a cloud instance that has 8 CPUs and 32 gigs of memory, I do not expect the heap to be only using 8 gigs of that memory. That is terribly inefficient. So you need to be changing your heap size if you're running your applications in the cloud to take advantage of the fact that you're paying for hardware, you should use it. Similarly, Bruno has this line, if you don't do anything, the default garbage collector in Java is probably serial GC. So if you've got one core available, serial GC is the default garbage collector. But also if you have under 1.8 gigs of RAM available, which is often the case in cloud instances, for example, you're also going to get serial GC, no matter how many cores you have available. And inside Linux containers, and this is another trick, again, I refer you to Bruno's presentation for a lot more exposition on this. But inside Linux containers, JVM calculates the CPUs available based on CPU.period, .quota, and .share. So anyone here who uses Kubernetes knows that, like cloud instances, you give them a certain number of millicores. Even if you're giving 2,000 millicores, you can end up having serial GC because the number of millicores reserved for the garbage collector brings it to under 1,000 available for your program, basically. I may be wrong there, but so choose the right garbage collector, choose the right heap size. You can use -XX active processor count to trick the JVM to know that there's more than one CPU available, by the way. So my recommendations for your heap is the heap should be between 75 and 85% of container memory or of available memory on cloud instances, right? You want to make sure that you leave a little bit of memory available for both your stack and program and also the operating system. But you can be pretty zealous with this, particularly if you're allocating a lot of memory for your cloud applications. I recommend using max RAM percentage rather than using an explicit amount of heap memory with XMC. Because you want to have that elasticity, that if you change instance types, your memory amount is also going to change without changing the command line. So that's your kind of basic starter, and then we're going to talk about the garbage collector. For cloud applications, and this is always going to depend on what type of application you're running, but I recommend G1GC or ZGC for latency-sensitive workloads. So ZGC has quite a lot of overhead, but it is a particular garbage collector that's tuned for low latency, and I have a graph showing this later, right here. This is an example of going from a workload going from G1GC to ZGC. It can have a dramatic impact on tail latencies, and for those of you who are unfamiliar, latency, time to response, tail latencies. You look at all of the queries that come in. You look at the 99th percentile or 99.9 percentile, and you might say, well, 99.9, I don't really care about that. But it's been one of the things in cloud application development in general is that a page or a query, like a user request, typically includes dozens or hundreds of these kind of tail latency specific operations. So your 99 percentile actually ends up being more like your median performance for your end users, right? If something takes whatever it takes in the 99th percentile, you're going to want to make sure for something like in-memory database, you're going to want to make sure that your tail latencies are really, really low. So care about your tails. And ZGC is, if you do care about tail latencies, then ZGC is the garbage collector for you. But most tuning depends on having some understanding of the needs of your applications. Most tuning needs to work with the specific needs of specific workloads. So one thing that you'll see is a lot of these changes that I talked about. For example, we talked about transparent huge pages, THP. And we've talked about latency in ZGC. Those are essentially, latency and throughput are essentially trade-offs, right? If you're using transparent huge pages, you're allocating large blocks of memory. That memory can be underutilized. So you're not using all of the resources available potentially in the server. The more that you add buffers, that's going to help for throughput. Think about the maximum throughput. This is an analogy I've been working on in my head. I'm going to say it out loud and we'll see if it works. The maximum throughput for, say, a motorway péage or a motorway toll booth is when every single booth is open and every operator is busy all the time. That means there's a tailback, right? That means that the only time that happens is if there's more traffic trying to get into the toll booth than the toll booth can process in terms of time. So you're exchanging wait times for throughput. So higher throughput, lower latency. It's typically a trade-off. So latency, and especially tail latencies, are a trade-off with throughput, and garbage collectors can affect tail latencies a lot. So you're going to need to do A/B testing on a lot of this stuff, right? It's not always as easy as use these settings and your performance will be good. May I have another show of hands? Who here has ever heard of TuneD? Okay, this is the one thing that I want you all to take away from this presentation. If your JVM is tuned to the max, but your operating system, you have left it as a default, you are leaving performance on the table. What TuneD does is it essentially says, okay, I am running this computer on Linux. I am running this computer as, and you can use a TuneD profile for Oracle that says, I am running this computer as an Oracle database. You can use a TuneD profile for desktop that says, I am running this computer as a desktop. The default is called balanced. And it balances power management and performance. Basically, the assumption is you're running on a desktop or you're running on a laptop. You can do a profile for power management, right? You can say, I'm running this on a laptop. I care a lot more about my battery life than I do about performance, so I'm going to run this as power management. And it's going to make sure that anytime anything on your laptop is not being used, it's going to turn off, which means that when you want to use it, it has to turn on. You've got a kind of a warm-up time. The default allows stuff to turn off in your computer a lot, right? It allows the CPU to go into power-saving mode. It allows you to put your network interface to sleep and your memory to. I don't know if that's true. I'm not going to say that. There are two profiles in particular that are specifically for, I am running this as a cloud application and I care about throughput, or I care about latency. Those are network throughput, which is, so what these profiles are is the first thing it does is it sets the CPU governor to say, I want to be this aggressive with my power saving of the CPU. That should be performance if you're running a cloud application. And then you say, I care about throughput or I care about latency. What network throughput does is it takes throughput performance. Throughput performance increases I/O buffers and turns off all power management. Network throughput is going to also increase the buffers for your network cards, RX and TX. Network latency takes latency performance, which, again, puts your CPU in high performance mode. It turns off all power management, and it optimizes for I/O wait times and CPU wait times. So it reduces the size of buffers. Network latency, same deal, reduces the size of network buffers. So you've got less throughput, but higher performance, lower latency. If you are not tuning your operating system for the workload that you're going to be running, what you've essentially got is you've got an operating system that the JVM is fighting against. The JVM wants to be high performance, and the operating system is not letting it because you're not getting all of the performance the system can make available. There are a few other kernel tuning options that you might look at. First, on Arm64, we support multiple memory page size. So 4K, same as x86, but we also support 16K and 64K memory pages. This is a boot time option for the Linux kernel, or I believe there's a sysconfig option. The positive of larger page sizes is that decreases cache turnover and it can reduce latency. The negative is that you end up potentially wasting resources because you've got bigger pages and maybe they're not as occupied, right? This is one that, this is a setting I came across that I was surprised that it had such a huge effect, but it does. For things like build servers, context switches. So I was watching a presentation by Gradle guy yesterday. I'm afraid I've forgotten his name, but he was talking about how a context switch for a developer takes 25 minutes. So if your build takes too long, you lose 25 minutes of productivity. For a build server, context switches happen in the kernel, right? And you lose not 25 minutes of performance, but you lose a lot of performance. Every time that you stop doing something, you have to switch to something else, and then your CPU goes back to what it was doing before. You lose performance in that. The context switches are a performance killer. They also affect tail latencies, right? So you can actually change the tick length, or the jiffy, I think it's called, of the Linux kernel. You can say, I want the Linux kernel to run at 100 hertz. That means I am only going to interrupt my CPU once every 100th of a second. So your CPU is a multi-gigahertz processor, right? But it's only going to be interrupted by the operating system once every 100th of a second. What that does for something like a build server or something where you've got compute-intensive workloads that you don't want to have that context switching, you have the ability to run interrupted for longer periods. It can be a 15 to 20% performance improvement for something like building a Linux kernel or building a compiler. It is quite impressive. So booting the kernel with config HC100 will improve the performance of things like your build servers. Okay, I am also going to call out another person, Monica Beckwith from Microsoft, has written a couple of really, really good articles on JVM configuration and how it interacts with the operating system for Arm64. She has done some performance testing on using THP with pre-touch, which we talked about earlier as a potential bug. She has seen an improvement in throughput figures of up to 21% at peak throughput and 17% in sustained throughput. And if you want to use that, you need to make sure that your user space can advise the operating system, I want to use, like user space applications, I want to use THP. So you need to add m-advised to the transparent huge page configuration. And one more tidbit is that you can turn off tiered compilation. So this is, like for those who are unfamiliar, the JVM can run interpreted, then it compiles, then it's got just-in-time, then it can compile to native. You can turn all of that off, and you can just have a higher upfront cost. I need to compile all my code to machine code, but it's going to run faster when it runs. So you can turn off this tiered compilation and ensure that you've got adequate cache for your JIT, and it can make up to a 1.5x difference in application performance at startup or getting to work. I'm going to call out a few tools. The Ampere Performance Toolkit is something that we recently open sourced, which can be used to do some analysis, static analysis of code that you're running, and can give you some advice on how you can improve its performance. Perf tools. So you've all seen flame graphs, which is a really good way of identifying how your program is spending its time. Can't speak highly enough of everything that Brendan Gregg has done. And gprof-ng, so the next generation of the GNU profiler, also includes Java and system profiling information. So highly recommend that as well. And I have 1.5 minutes left. If there are any questions, shout out your question. I'll repeat it. Yep.
Which ones of these optimization improvements that you talked about are ARM-specific, and which ones do you think also apply to other architectures like, for instance, RISC-V? That's my first question.
Right. So the first question was, what's ARM-specific and what's RISC-V, potentially?
Or other architectures.
Yeah.
Second question, that's one towards Ampere. You're making a lot of exciting hardware, mostly the server front. For developers to get their hands on it, it's quite unaffordable.
Okay.
Going to release a workstation or developer board or product anytime soon?
And the second question is, when is Ampere going to release a developer workstation or board sometime soon? Well, we have got, we've made quite some progress in terms of, you can go to System 76 and get a desktop form factor today. They're out there, and they're, I mean, 2,500, 3,000 euros. But that's a pretty competitive price for what you're getting in terms of the processor. You're getting 128 cores, Arm64 processor. We're not an SBC company. I am unapologetic about that. We're not an SBC company. Our goal is not the low end. Our goal is data centers and clouds, which makes developer boards a little bit more complicated to get to that price point. But we have had some success in both. You can get a server, an Ampere Ultra Max server, for 2,500 euros now. And you can get the desktop form factor for, I believe, about the same, 2,500. It's not perfect, but it's what we have available at this point. On the rest, everything in the second part was not platform specific. Everything in the first part, I believe, needs to be redone for the equivalent of RISC-V or other architectures. They're essentially, like going back to the intrinsics part, they're essentially ARM-specific implementations of the accelerators that are there for x86 already. And I'm out of time. Thank you very much, everyone. And I'll be here for a minute or two if you have any questions, if you want to come down and ask them.
All systems are nominal. Initialize Genesis sequence.